As promised, here is a video for section 8.2, which might be the most important section in all of geometry, because this is the section where you get to learn an entirely brand new section of math. So we're going to talk about what is trigonometry today. We're going to talk about how to find what we call the trigonometric ratios on a right triangle. And we're going to talk about why these kinds of calculations can be useful to us and they can add to the body of math that we already know. So first off, let's run through what we've done before. We talked about the Pythagorean theorem and what that can do for us, and the fact that if we know the Pythagorean theorem, if we know two sides of a right triangle, we can find the length of the third side. So that's where we started. We also talked a little bit about special right triangles yesterday, and in these special right triangles, we could do more stuff. Because of the patterns in how their sides were related to each other, we were able to find the two missing sides if we just knew one of the side lengths. So we were able to find double the information and start out with less. So the first thing I have to tell you today is that calling those special right triangles was kind of a lie. There's nothing special about special right triangles, and instead, they happen to be common right triangles. So we talk a lot about 45, 45, 90 right triangles because we see them a lot. We talk about 30, 60, 90 right triangles because we see them a lot. And being able to memorize the relationships between the sides of them can be really helpful in a triangle that we see a lot. However, they are not the only kind of right triangles that have knowable and always the same relationships between their side lengths. And in fact, every single right triangle that you could ever make has a known relationship between its side lengths. And if we wanted to, we could memorize all kinds of different ratios. We could memorize if our right triangle had 90 degrees and 10 degrees. We could memorize if our triangle had 50 degrees and 40 degrees. So every single triangle that we have will have a relationship that we could diagram out just like we did for our special, quote unquote, right triangles. What's the problem with that? Well, the fact that there is such an example for every kind of right triangle means that there are infinitely many, because we could make this all different numbers of degrees. And we obviously cannot memorize infinitely many right triangle ratios. So what we do instead is we have a system, and it's a system for how we represent the relationships between the sides of a right triangle, no matter what angles it has. So we're going to represent trigonometric ratios, and we're going to define them as the ratios of side lengths in a right triangle. Oops, the ratios, if I could spell, of side lengths in a right triangle. So what do we mean by that? We mean if I have a right triangle and I think about the side lengths of this right triangle, there's my right angle, I can talk about how this leg is related to the hypotenuse, or how this leg is related to, or the hypotenuse is related to this leg, or how the legs are related to each other in that right triangle. So what I'm going to do here is I think that I am going to label the sides and angles of my right triangle, and I think maybe I will call the vertices P, Q, and R. And if I called those vertices P, Q, and R, then the typical naming convention is to call the sides opposite of them the lowercase version of those letters. So I have lowercase p, lowercase q, and lowercase r as my side lengths, opposite of capital P, Q, and R as my angles. For this, we're going to have to do some imagining. So our first trigonometric ratio is called sine. And to imagine what sine is, we're going to need to shrink ourselves down. So I want you to shrink yourself down until you're so short that you can stand on the angles in this triangle. And I want you to move your little shrink self and stand on point P. So pretend that you're standing on that in real life. And if I'm standing on point P, the side lengths of my triangle are related to this point in a certain way. I have a side that is opposite of point P. I have a side that is adjacent to point P, right next to it. And I have a side of the triangle that is the hypotenuse. Now, the hypotenuse is also adjacent to point P, but it's being the hypotenuse makes that more important. So R is the side adjacent and P is the hypotenuse. Sine, cosine, and tangent are all different relationships between those three sides. So the first one, we call this sine. Sine is the relationship between the opposite and the hypotenuse in a right triangle, and we represent it as a fraction. So I can also abbreviate it. I tend to abbreviate it so that I can memorize better. Sine equals opposite over hypotenuse can be abbreviated as S equals O over H. So what does that actually mean? Let's look at the triangle I have over here and imagine my shrink self standing on P. So what I'm calculating here, what I can record is the sine. We abbreviate sine as 3 letters, S-I-N, but we pronounce it sine every time. So what I'm looking at is the sine of side P. And the sine of side P is represented by the fraction of the opposite side over the hypotenuse. So if I'm standing on P, the opposite side is lowercase p over the hypotenuse, which is lowercase q. So the sine of P, that weird idea, ends up just being a number. And it's the number we get when we divide the length of side P over the length of side Q. That's going to become more obvious as we do some examples later. The next trigonometric ratio is cosine. And cosine is represented by the adjacent side over the hypotenuse. I can abbreviate this one as well. I can write C for cosine equals A over H. So cosine equals adjacent over hypotenuse. If I am standing on point P and my shrink self is going to find the cosine of point P, so COS for cosine, then I'm going to say I need the fraction that represents the adjacent side over the hypotenuse. So R over Q will represent the cosine of P. And then the tangent is our last trigonometric ratio. That is represented by opposite over adjacent. Or as an abbreviation, T equals O over A. And so if I'm standing on point P and I want to find the tangent of that point or the tangent of that angle, then I would write TAN for tangent of point P equals the opposite side over the hypotenuse. The opposite side over the adjacent. So P is the opposite side and R is the adjacent side. So that fraction, P over R, is going to represent the tangent of angle P, right? The best way that I know of to memorize these is to use the 3 abbreviations that I have here and create a word out of them. So think of the word and memorize the word SOHCAHTOA. And if I remember the word SOHCAHTOA, then I will remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So I'll have all 3 of those pieces of information in my brain. So make sure that you memorize SOHCAHTOA. Big deal thing right there. So again, we'll talk about what this all means, why is it important, and how do these really represent the ratio between the side lengths. In example 1, we're going to talk about why it's important to know trigonometry because it's universal. So the question here is, how are the sines of two different angles with the same measure related? So I'm looking at two triangles here, and I notice that they're both 30, 60, 90 triangles. So these triangles have the same angle measures. However, they're different triangles. This triangle has different side lengths than this one. They're similar triangles. So we want to try and figure out if the side lengths of my triangle affect the sine of the angle. Okay? So I'm going to start with this first triangle. And I'm going to maybe use 30 degrees as my marker. So I'm going to walk over to 30 degrees with my little shrinky self and stand right here on the 30-degree angle. And I'm going to calculate the sine of that 30-degree angle by writing the sine of 30 degrees is equal to, and then I go back to my abbreviations and I say, okay, sine is opposite over hypotenuse. The side that is opposite the 30-degree angle is 5 over the hypotenuse, which is 10. So the sine of 30 is equal to 5 over 10. 5 over 10 is equal to 1/2. This is interesting. Sine, cosine, and tangent will just be a number. The sine of 30 is 1/2 in this case. And that represents that the opposite side is half the length of the hypotenuse, which happens. The opposite side is half the length of the hypotenuse. Let's take a look at this other 30, 60, 90 degree triangle and calculate the sine of this 30 degrees. So we're going to write the sine of 30 degrees equals, and then if we're standing on 30, the opposite side is 3, and the hypotenuse is 6. So it equals 3 over 6. Well, guess what? 3 over 6 is equal to 1/2. Because the opposite side is half the length of the hypotenuse. And that's going to happen for every 30-degree angle. The 1/2, the sine of 30, becomes a property of that number. Every number has a sine, a cosine, and a tangent. And they're always going to be consistent. Every time I calculate the sine of 30, it's going to be 1/2. So we can conclude here, what we learned, which is that the sine of two of the same angles are the same. The sine, S-I-N, of two of the same angles are the same. And the question here is that true about cosines? And is that true about tangents? And the answer is yes, of course. If I calculated the cosine of every 30-degree angle, it would come out the same, because the relationship between the adjacent side and the hypotenuse of every 30-degree right triangle is the same. Tangent of 30 will always come out the same. All of our numbers will come out the same for every angle that is the same. So we can say yes, and for tangent as well. Okay? So that means that there's this whole new set of 3 numbers that are a property of every number. 30 has a sine, a cosine, and a tangent. 50 has a sine, a cosine, and a tangent. 27 3/4 has a sine, a cosine, and a tangent. So how are we supposed to memorize all these? Do we have to draw triangles every time? Luckily for us, our calculator is able to do sine, cosine, and tangent, and it sort of has those ratios, those relationships programmed into it from the start. So one thing that's really important is to make sure your calculator is in degree mode. Your calculator will only work in degree mode for trigonometry for this class. It might be in radian mode when you look at it. And when you look at the top bar of information on your calculator, it'll tell you what mode it's in. If it's not in degree mode, hit the mode button and go down to the 4th line to change it into degree mode so that you can do your calculations. So let's work a little bit more by hand before we get into those calculations. Let's come up with some more of these ratios to explain what we are looking at when we talk about sine, cosine, and tangent. So here it says, what are the sine, cosine, and tangent ratios for angle H and angle F? So I'm going to go ahead in here, and I'm going to write in the sine ratios for H, the cosine of H, and the tangent of H. Oops. As well as the sine of F, the cosine of F, and the tangent of F. And so for each one of these, we're going to figure them out. So to find the sine of H, I'm going to move my little shrinked self over to H and stand here. And I'm going to remind myself that sine is opposite over hypotenuse. So opposite side is 12, hypotenuse is 15. The sine of H is 12 over 15. If we wanted to, we could reduce that fraction to 4 over 5, right? The opposite side is 4/5 the length of the hypotenuse. The cosine of H means we're going to stand on H and look at adjacent over hypotenuse, which is equal to 9 over 15, which simplifies to 3/5. Tangent means we're going to look at opposite over adjacent, which is 12 over 9, which is equal to 4/3. So again, what that means is if I'm standing on H, the opposite side is 4/3 of the adjacent side. And that will change if my angle measure changes. Then for sine, cosine, and tangent of F, I'm going to take my little shrink self and walk it over to F. And I'm going to record the same information. The sine of F is opposite over hypotenuse. So that is 9 over 15, or 3/5. The cosine of F is adjacent over hypotenuse, so that's 12 over 15, or 4/5. And then the tangent of F is opposite over adjacent, so that's 9 over 12, or 3/4. All right? Now you might have noticed that this question did not ask us to find the sine, cosine, and tangent of G. And that's a really important thing to realize, because G is the right angle. And we cannot do trigonometry while we're standing on the right angle. Think for a minute about the reason why that might be. Why can't we do trigonometry if we're standing on the right angle? Pause the video to think about it and then come back and I'll tell you the answer. So the reason we can't do trigonometry while we're standing at the right angle is because the opposite side and the hypotenuse are the same side. And we have two sides that we could consider to be the adjacent side. So there's no clear-cut opposite, adjacent, and hypotenuse if we're standing on G. The only time those definitions are, or those positions are defined is if we're standing on H or we're standing on F. So again, I repeat, we cannot do trigonometry while we're standing on the right angle. One thing you might notice when you look at the information in this example is some patterns. And if you think you see a pattern, you probably do see a pattern. We have so many patterns in trigonometry that I don't think that I could name all of them for you if I spent the rest of the year doing it. So you're probably going to see lots of little patterns in our trigonometric ratios. We might point out some of them. We won't point out all of them because that would be impossible. But for the next few years in math, you're going to spend a lot of time working on trigonometric ratios, and you're going to find more of those relationships and patterns as you go. The next thing I want to do is I want to take a look back at our special, quote, right triangles for a minute, and I want to calculate their trigonometric ratios. Because we were able to use a framework of x, and x root 2, as well as x, 2x, and x root 3 to talk about these side lengths and how they're related to each other. But they will also have really common trigonometric ratios. And because we see 30, 45, and 60 a lot as angle measures, it's nice for us to know the exact values of their trigonometric ratios. So first we'll look at this 45, 45, 90 triangle, and we'll calculate the sine of 45, the cosine of 45, and the tangent of 45. So if I'm standing on the 45 degree, I could be standing on this angle or this angle, it doesn't matter. And for sine of 45 degrees, I've got opposite over hypotenuse. So 1 over the square root of 2. However, we're going to want to rationalize that denominator. So I've got to multiply that fraction by the square root of 2 over itself. And I end up with the square root of 2 on the top over root 2 times root 2, which is just 2. So the exact value of the sine of 45 is the square root of 2 over 2. It's also, of course, a decimal approximation. The cosine of 45 happens if I'm standing on 45. I do adjacent over hypotenuse. That's the same thing. That's 1 over the square root of 2, which will simplify to the square root of 2 over 2, same as the sine. And then the tangent of 45 comes when I'm doing opposite over adjacent. That's going to be 1 over 1, which is 1. So the exact values of sine, cosine, and tangent of 45 are right there for you. We can also find those same values for 30 degrees and 60 degrees. So sine of 30, cosine of 30, and tangent of 30. And we'll use this triangle that's got our placeholder values for the side lengths. So if I'm standing on the 30, opposite over hypotenuse is just 1/2. If I'm standing on the 30, adjacent over hypotenuse is the square root of 3 over 2. And the tangent of 30 is opposite over adjacent. That's 1 over the square root of 3. But when I rationalize the denominator by multiplying both sides by the square root of 3, I get the square root of 3 over 3. Then finally, I'm going to go ahead and find the trigonometric ratios for 60. I'm going to find the sine of 60, the cosine of 60, and the tangent of 60. So if I stand on the 60 and I think opposite over hypotenuse, I've got square root of 3 over 2. And if I stand there and I try and find adjacent over hypotenuse, I've got 1/2. And if I go to the tangent of 60 and I try to find opposite over adjacent, I have the square root of 3 over 1, which is just the square root of 3. So those are the exact values instead of decimals for my most common sine, cosine, and tangent. And as we look at these, we can see one of the next properties, one of the only patterns we're going to discuss in our trigonometric ratios. The question here is, how are the sine and cosine of complementary angles related? Remind yourself that complementary means add to 90. That's supposed to be a plus sign. They add to 90. And for example, I have some angles here that add to 90. I have 30 and 60. So when I compare the sine and cosine of these complementary angles, what do I notice? Think about it. I notice that the sine of one is equal to the cosine of the other, and the cosine of one is equal to the sine of the other. It's like they traded. That's the pattern we want you to notice, and we want to write that down. The sine of one is the cosine of the other. The sine of one is the cosine of the other. So how does that benefit us? Well, that means that we can rewrite equivalent expressions. If I have something that's written with cosine, but I want to find it in terms of sine instead, I want it to change to the sine of a number, I can do that. If I see cosine of 70, I can say, well, I know that's going to be the same as the sine of the complementary angle. The complementary angle of 70 is 20, since 70 plus 20 add to 90. So cosine of 70 and sine of 20 should be the same number. If I have the sine of 34 and I want to write it as the cosine of a number, I just figure out the complement of 34. 34 plus 56 is 90. So the cosine of 56 and the sine of 34 are equal. As you get further into math, it is sometimes required to change your trigonometric ratios into other ones so that you can simplify expressions. So that's the end of our very, very basics. What is sine? What is cosine? What is tangent? But what I'm betting you want to think about now is how do I use those? Why am I using or finding sine, cosine, and tangent at all? And the reason for it is because now we're going to be able to treat every triangle like a special right triangle. Instead of needing to know two sides to find the length of the third side with Pythagorean theorem, I now only need to know one side of my right triangle to find any information about the other sides. And I can do that using trigonometry, since trigonometry represents the relationships between my sides for any given angle measure. Here's an example. This is my favorite problem. A plane takes off and flies at a 12-degree angle. Is that angle sufficient enough to fly over an 11,088-foot mountain that is 12.5 miles from the runway? Or does the plane need to increase its angle of ascent? I love this question because if we get it wrong, the plane crashes into the mountain. So if that's not enough real-world consequences for you, I don't know what is. So here's what we're going to do. We're going to look at the right triangle we've presented with, and we're going to find an angle to stand on. We're going to find our beginning angle. Here we have 12 degrees, and that works as a beginning angle. Then I am going to look for what information I'm trying to find and what information I know. In this case, I want to see how high the plane gets at the end of 12.5 miles. So I'm looking for x. X happens to be the side opposite of 12 degrees. 12.5 is the side length that I know. That happens to be the side adjacent to 12 degrees. So to figure out what trigonometric ratio I'm going to use to solve this problem, I think to myself, which trig ratio relates opposite and adjacent? And I realize I'm going to use tangent. So I'm going to write an equation that represents the tangent of the angle I'm standing on. So the tangent of that angle in question, which is 12 degrees, is equal to the length of the opposite side, x, over the adjacent side, 12.5. And then all I need to do is solve this equation. So I'm solving for x. I want to get x on its own, which means I'm going to multiply both sides by 12.5 to get it out of the denominator. Now I have 12.5 tangents of 12 equals x. The cool thing about the tangent of 12 is that it's just a number. It just represents a decimal value. And the even cooler thing about the tangent of 12 is that our calculator already knows it. So with your calculator in degree mode, all you need to do is type in 12.5 tangent of 12 into the calculator. And that's going to tell us then that our answer is 2.66. Now what is that in units? Looks like I used miles for my calculation. So that's 2.66 miles. Our airplane is going to be 2.66 miles high at the end of that ascent. Is that enough to fly over an 11,088-foot mountain? I'm not sure. I have to then calculate the conversion factor between miles and feet. So if you don't know, one thing that you should know that you should be memorizing is the conversion factor between miles and feet, just because we see it very often at this point in school. 1 mile is equal to 5,280 feet. I want you to memorize that, okay? So we'll use that conversion factor. If we have 2.66 miles, and each mile has 5,280 feet in it, then altogether we have 13,992 feet. What does that tell us? That tells us that by the end of its ascent, the plane will be 13,992 feet in the air. Is it above the mountain? It's above the mountain. So the plane does not need to increase its angle of ascent. It doesn't need to increase its angle because this angle is perfectly fine to get it over the mountain. So we can just say that that is sufficient. That angle will work. It'll get us over the top. And again, notice what we just did. We only knew one side of our right triangle, and we were able to find the other side. We didn't need two sides anymore. We've done twice the work with half the amount of given information. Let's keep going. Let's do some more examples. So the next one I want you to do is a similar problem. They're not all about airplanes, but in this case, two things are different. Thing number one is that you don't have a diagram, and that's really important. We always need diagrams when we're using trigonometry. So we're going to make ourselves a diagram. We've got another plane. It's climbing at 5 degrees. So here's the ground. Here's the 5-degree angle. And it flies 20 miles through the air as it climbs. So here's our 5 degrees. If it flies 20 miles through the air as it climbs, it's flying. So its air distance is right there, 20 miles. And it's still a right triangle because the ground and directly above the plane is still a right angle. We want to know what is the altitude of the plane to the nearest foot. So altitude would be the height of the plane. So if this is my information, I start by finding my angle in question, that's 5 degrees, and I stand right there. And I say if I'm standing on this angle, which sides are going to be related? Looks like I'm looking for the opposite side, and I know the hypotenuse. So if I'm looking for the opposite side and I know the hypotenuse, then I am going to use the trigonometric ratio that represents opposite over hypotenuse, and that is the sine. So I'll write the sine equation. The sine of 5 degrees equals opposite side x over hypotenuse 20. And I'll solve for x. So I'll multiply both sides by 20. Sine of 5 equals x. And I'll just go to my calculator and I'll bop in 20 sine of 5. And the calculator tells me, hey, that's 1.74. So 1.74 is going to be x. And what that means for me is that's going to be 1.74 miles because my original diagram had 20 in miles. I need to know the altitude to the nearest foot. So just like before, just as a separate extra little thing to remind you about in this section, I am going to use my conversion factor. So 1.74 miles times 5,280 feet in each mile gives us 9,204 feet of altitude for that plane. We're going to work with a lot of different problems where we're setting up the diagram, and we might be using the sine, the cosine, or the tangent to find the information that we need. So that's crazy and exciting enough. But not only that, there's more. We can also use trigonometry backwards, and we can use it to find the missing angle measures in a right triangle. Now, this is something we've never, ever been able to do before. I don't know how to find an angle measure. We have no way of finding angle measures yet. However, that all changes today. So here I have a right triangle, and I have two of the sides. I'm hoping to find the measure of angle A and the measure of angle B. So I'm finding the actual angle measures of this triangle, something that I've not done before. I am going to start maybe with angle A, and I'm going to say, all right, if I'm finding angle A, I'm going to stand on angle A. If I stand on angle A, I have two sides that I know. I know the adjacent side, and I know the hypotenuse. And I ask myself, which of my trig ratios represents the ratio of the adjacent and the hypotenuse? And that is my cosine. So then I'm going to go ahead and I'm going to write a cosine equation. The cosine of angle A. I don't know angle A, but the cosine of it is adjacent 1 over hypotenuse 4. So the cosine of A is 1 over 4. But I don't really want to find the cosine of A. I just want to find angle A. I want to find the measure of that angle, not its cosine. So I want to find a way to get rid of the word cosine and just have an A here. I want to essentially uncosine my angle. And lucky for us, there is a way to undo cosine. It's called inverse cosine. And there's a button for it on your calculator. It's the button right up above the cosine button. You just hit second and then inverse cosine. If I take the inverse cosine of the cosine, oops, let me use a different color, cosine of A, it gets rid of it. So the inverse cosine of the cosine cancels itself out, and I'm just left with angle A. But of course, if I took the inverse cosine of one side of the equation, I'm also going to need to take the inverse cosine of the other side of the equation. So on the other side, that looks like the inverse cosine of 1/4. How do I perform that calculation? Lucky for us, the calculator knows. So all I need to do is go to my calculator and type in the inverse cosine of 1/4. And it tells me. It tells me that A is equal to 75.5. I remind myself what A was. A was an angle. So A is 75.5 degrees. This angle of my triangle is 75.5 degrees. We just found an angle. We've never been able to do that before. Of course, the last angle in this triangle then is a lot easier to find because I already know this angle and I know this angle. So all I need to do to find B is say I'm going to take 180 minus my right angle 90 minus 75.5 and find that angle B is 14.5 degrees. Exactly. So the same way that we found the angles in this example, we're going to find the angles in the next example, the angle P and the angle Q. So if I start by angle P, I'll stand right here, and I'll take stock of what I know. If I'm standing at angle P, I know the opposite side, and I know the adjacent side. Tangent is what I'm going to use, because tangent is equal to opposite over adjacent. So I'm going to say that the tangent of the angle I don't know, P, is equal to the opposite side, 2, over the adjacent side, 3. I don't want the tangent of P, I just want angle P without the word tangent. So once again, I am going to take the inverse trig function. I'm going to take the inverse tangent, and again, that's a button on your calculator right above tangent. Inverse tangent of the tangent of P is equal to the inverse tangent, because I've got to do it on the other side as well, of 2/3. So on the left, inverse tangent of tangent cancels itself out, and I'm left with angle P. On the right, I can just bop that in my calculator and say that, okay, the inverse tangent of 2/3 is 33.7. So angle P is 33.7 degrees. And then angle Q will be what's left over, right? 180 minus 90 minus 33.7 gives us 56.3 degrees for angle Q. Oops, not the side length. It's an angle. Just like that. It's like magic. I can find missing side lengths using trigonometry. I can find missing angles using trigonometry with way less information than I was able to before today. So we're going to do some practice, and we're going to spend some time learning how to find different sides and angles in a triangle before we move on. Let me know, of course, if you have any questions. Thank you.